Hey everybody, my name is Ted Petrou and I'm going to be doing this broadcast on Introduction to Machine Learning in Python with Scikit Learn. So a lot of people signed up in the last day or so, so I'm gonna give us just a little bit of time, maybe a minute, and then I'll formally start the presentation. If you want to download the material while we're waiting, you can look in the chat portion of the GoToMeeting panel, and you'll see a link that I provided that you can go to on GitHub and download the material. So if you want to do that now, you're more than welcome to. And this is exactly the page I'm talking about. And if you go and click on clone or download, you'll be able to, I would just download it since that would be the easiest thing to do. Just go ahead and download as a zip, and then you can have access to the material. So the material is actually in this folder, Intro to Scikit Learn. There's other tutorials in here. I have a tutorial to Introduction to Statistical Learning, which is another machine learning book. But specifically, this tutorial is in this folder right here, Intro to Scikit Learn. And we'll be working in this particular Jupyter notebook called Intro to Machine Learning. Okay. And if you have any questions, just go ahead and ask, put the questions in the little question box, and I'll get to that at the end of the tutorial. All right, well, let's just get started. So again, my name is Ted Petrou, and I'm going to guide you through this tutorial on an introduction to machine learning in Python with Scikit Learn. This is going to be a very gentle introduction to machine learning in Python. We're going to focus on the application of machine learning and actual usage of Scikit Learn. I am doing this through a company called Wintellect, and they have professional training in a variety of different courses. Here are some of Wintellect's core services. They do consulting, they do lots of instructor training, and also on-demand training. They have written, their employees have written several books. They're particularly well known in the Microsoft world. And as you can see in this slide, they've partnered with Microsoft in a variety of ways. All right, so let's get into it. Just a little bit about me before we begin. I'm the author of Pandas Cookbook. Pandas is a library that does data analysis in Python. This book came out late last year, and Pandas is essentially the tool you use to do a lot of the pre-processing before you do the machine learning. We're not going to concentrate on Pandas in this tutorial. I founded a company called Dunder Data, and I teach classes, data science classes, and several of them are available through Wintellect. So if you check out Wintellect, you'll be able to see my professional training courses. I'm also a founder of the Houston Data Science Meetup. So I was born and raised in Houston, and I started that meetup. And if you're in Houston, I would highly encourage you to go. So a quick little outline of what we're going to do today. We're going to briefly talk about what machine learning is. We're going to go over what a typical workflow will look like in Python. We're going to do an overview of Scikit Learn in slides. And then we're actually going to, hopefully the majority of the time will be spent actually demoing Scikit Learn in machine learning in a data set. So Again, this is primarily going to be application-based, not theory-based. So we're going to be practicing the commands in Scikit Learn. And then I'll take questions at the end. All right, so a very brief overview on what machine learning is.
Ted, can you excuse me 1 second? Can you put the link to the materials into the chat window? Because some people can't access it in the folders, or in the GitHub that you sent us.
I can put the link is in the chat. I'm not
It is?
sure which.
Okay, perfect.
Yeah, so if you go to the chat, you should see the link. Yeah, I can repost it again. I don't know if
Yeah, because I can't see it. Oh, there it is. Okay, thank you.
Okay, so I've reposted the link. All right, so a very simple definition for machine learning is a process by which a machine, which is going to be our computer, learns how to be successful at a certain task without being explicitly programmed to do so. So, and what does that actually mean? To begin with, it learns by being given data. So you have to have data in order to do machine learning. If you don't have data, you cannot do machine learning. And to be successful, you have to define a particular metric on what success means, or else the machine won't learn on what to target and how to get better at what you're trying to target. Many people have developed particular algorithms that use this definition of success and eventually build a model that will transform the input, which is your data, into an output, which is what you use as the intelligence from the model. And of course, the benefit of machine learning is that whenever you get in new data, you can use your model and you can transform it into an output upon which a decision can be made. All right, so some simple examples of machine learning. So if you have Google Translate on your phone, it's recognizing your voice and translating it into a different language. Something a little bit simpler, predicting GDP of a country, given certain input parameters. Some machines can learn to play games such as poker. Discovering topics in news articles, and recommending different products to buy. So those are very simple examples of machine learning that are used today. What makes a good machine learning model? So first of all, it has to be better than a default guess. So that means, for instance, if we are playing poker, you must do better than just to call every time, if you know about poker. Or if you're trying to guess whether a transaction from your credit card is fraudulent or not, and you guess no every single time, that's not a very good model. So that's not going to be machine learning. The opposite of that is that it needs to generalize to unseen data. So if your model does very well on one particular data set, but does not do well on newer data, then that's called not generalizing or not or overfitting. We want to try to minimize that and not memorize historical data. And also, developing this model must be cheap enough that it is less than the actual value it provides. All right, so some simple types of machine learning. We're going to talk about the two main types, which is supervised learning and unsupervised learning. Supervised learning is when you have a given target that you know you're trying to predict. And these targets can be either continuous or they can be categorical. So a continuous target is something like GDP, which is a number, and is called regression. A categorical target would be like the name of an image you're trying to recognize, and that is called classification. Unsupervised learning doesn't have a target, and it's more concerned with finding underlying structure within data, trying to group, for instance, like news articles together. But today we're actually just going to do supervised learning because of time constraints. All right, so here's a typical workflow for beginners, and this is exactly how my tutorial is set up. We're going to grab a data set, usually one single file, a CSV. Here are 3 sources you can go to get data sets that are very good for machine learning. Kaggle data sets, data.world, data.gov is for US government data. We're going to read the data into pandas. We're going to do some cleaning of the data. We're going to do some basic exploratory data analysis with statistics and visualizations. This will help us define a problem of what we're trying to, how we're trying to learn from the data. We're going to take that data into Numpy, which forms the basis for both pandas and Scikit Learn. And then we're going to train and evaluate the model with Scikit Learn. So the last thing we do in a beginner's workflow is train and evaluate the model in Scikit Learn. We're basically going to very quickly go through the first few of these steps and get to the bottom. Okay, so a brief overview of Scikit Learn. It's the most popular Python library to build basic machine learning models. It's easy to use, and you can train a model in just 3 lines of code. So a lot of people, you out there have probably heard about deep learning. Scikit-learn does not focus on deep learning. That's not its primary focus. If you want to do deep learning, you should look at TensorFlow or Keras. So like I said, it's built directly on top of NumPy. It uses the NumPy array as its data structure to contain all the data. And it has a whole host of other tools besides machine learning models that can help you with data preprocessing and model evaluation. All right, quickly some vocabulary. All right, so when we're training a machine learning model, we need data. The data is stored in a 2-dimensional, our input data is stored into a 2-dimensional NumPy array. We usually give it the name x as the variable name. Inside this input array, each column is known as a feature. Each row is known as a sample. And then what we actually use to build our machine model is called an estimator. So Scikit-learn uses this term estimator. This is a very important word. It's basically the main object that does the training and the predicting and also the scoring. So we'll talk a lot about estimators today. So particularly in supervised learning, each row, each sample has a target, and that target is either going to be categorical or continuous. That's going to determine whether we have classification or regression types of machine learning. We can also call this a label, and all these labels are separated into their own array, and we give this name usually Y. So if you look at the Scikit-learn documentation, you'll see X and Y used all over the place. X for the input and Y for the target or output. Okay, so a few gotchas before we get started on Scikit-learn. You cannot have any missing data in your input or target arrays. So you have to fill in missing data in order to use your array in Scikit-learn. All your input data must be numeric, and it must be a 2-dimensional array. So you can't use a 1-dimensional array or a 3-dimensional array. You must use a numeric 2D array. That means you can't have strings in your array. So we'll talk about string encoding a little bit later, but you must turn the strings into numbers in order to use Scikit Learn. All right, so our example is going to use the Ames housing dataset from Kaggle. It's used as a beginner competition. We're going to use a subset of the columns. It's compiled by Dean DeCock from Ames, Iowa, from 2006 to 2010. Originally had 79 columns or features and over 1,400 samples. We're just going to look at 8 features to make things simple, and we're going to try to predict the sale price of these homes. All right, and we're going to evaluate, as I said, every machine learning model needs some sort of success metric, and so we're going to use R-squared, and I'll explain R-squared later. All right, so this is how we get started, especially as a beginner. This is a very common workflow for beginners. So what you're going to do is, and I'm able to run code in these slides, we're going to read in our data stored in this housing data set. And this is just the top 5 rows. All right. Up here, we're just importing in pandas and NumPy and matplotlib for plotting. But here's our first 5 rows of our data set. We're looking to predict over here the sales price based on these features. So we're going to try to learn from these features. Okay, so like I said, it's good to do some, it's actually good to do a lot of exploratory data analysis, but since we're focusing on Scikit Learn, we're going to do just a small amount here. I've done, in this particular line of code, we're going to find the average sale price by the overall quality. So overall quality is a metric that's from 1 to 10. And so I've grouped by this overall quality, and you can see the sales price looks like there's a direct relationship between quality and sales price. As quality increases, sales price increases. So this is just a basic way to do some learning just manually, not automated. All right, now if we run this same grouping but by a different variable, say garage type, and we look at the average sale price by garage type, we can see there's about 6 different garage types, and this garage type variable is not giving us much information. Okay, so this is just this is some pandas. So I'm not really explaining it because I want to get to the Scikit Learn part. I'm just showing you some basic EDA that we can do. All right, so this is a plot. I'm plotting the ground living area versus the sale price. And you can see here that as the ground living area increases, the square footage of the home, essentially, the sales price is also increasing. So this is has a positive relationship. And this is just another way of grouping the same data. I've grouped the square footage, the ground living area, into 10 different equal size bins. And as you can see, as the square footage increases, we get a higher sales price, and it looks like there's some outliers over here that are very large houses, but very low price at the same time. Okay, so that's just some basic EDA just to say that we've done it. I obviously recommend doing much more, but our focus is on Scikit Learn, so let's go there. Okay, so before we actually do any machine learning, we have to prepare our data. And one of the main things we have to do to prepare our data is to remove missing values. So first, I'm going to find out how many missing values I have in each one with this command. So I have some columns with some missing values. This lot frontage column has 259 missing values. Garage type also has 81 missing values. All right. So lot frontage is a continuous variable. And so I'm going to just replace all the missing values with the median. There's lots of literature on what to do with replacing missing values. I'm just going to do something simple and replace it with the median. You can even do machine learning to try to figure out what the missing values are. So I'm going to make a replica of my data set just so I don't touch the original. And these 2 lines of code, again, I'm just getting the median right here. And I'm going to store that median, or I'm going to fill in the missing values. This is a command from Pandas. So I'm in Pandas here, I should say. I'm using a data frame. I'm going to fill those missing values with this number 69. So 69 is the median for lot frontage. So I've ran that cell. Now, garage type is a categorical. So categorical means it has discrete values, usually means strings. And we can see the values over here. It is missing 81. It is missing 81 values. So I'm actually going to fill this in with actually the word missing. So there's different strategies for how to fill in missing values. I'm just showing you a basic strategy. I'm turning the missing values into something that's just called missing. And you can fill it in with the most common. Maybe you could have made it attached. You could put random values in there. There's different strategies here. Okay, so now that I filled in the missing values, I can recheck how many missing values I have, and I don't have any more missing values. Okay, so my data set is devoid of missing values, so I've remedied that problem. Just quickly backtracking, I didn't mention this earlier, so columns are also either continuous or categorical. Categorical just means that they have distinct values and they're usually strings, though they can be numbers as well. Continuous features can take on any value and they're always numeric. Okay, all right. Okay, and this is what we're going to do next. We're going to, Scikit Learn does not take internally handle columns that are strings. And this is a big thing for Scikit Learn. You have to convert all of your data into numeric, all of your X data into numeric. And Pandas has a great function to do this. It's called get dummies, and I'll show you that next. Okay, so this get dummies will turn every unique value of a column into 0 or 1, and it's much easier explained if we just use it. So as you can see, I'm passing in the whole data set into this get dummies function. And get dummies will only change the categorical columns. It'll leave the continuous columns the way they are. All right, so, and if I show you the output, it'll make a lot of sense. So, for instance, this roof material column had several different types of material, and now they're each their own column that are zeros or ones. So the roof material, what Pandas does, it appends the unique value of each column to the column name and creates new columns. That's what get dummies is doing. So it's created all these new columns for roofing material, as you can see. All of these are all different kinds of roofing material. And for the current row, it has the roofing material of this, whatever this means, this comp SHG shingle or something. So there's zeros in everywhere else except for that. So that's what get dummies is doing. It's taking these string columns, the categorical columns, and it's turning them into 0 or 1s. Now we go to the next variable, garage types. You can see all the garage types there are. And again, it's doing the exact same thing. It's making 0s or 1s for the different types of garage types. So this current particular row has a garage type of attached. This row down here has a garage type of detached. Okay. So it had 2 categorical variables and it changed them. Now we can actually make it change. You could these are actually categorical variables too, even though they're numeric. But we're not going to change them for now. All right, so let's check our data types that we have in our housing data set now. As you can see, we don't have any string data types. Everything is in integer except for this lot frontage, which is a float. So we're good. So we've successfully created numeric data, which is what we wanted. Now, if we looked at our original data set, you can see that we had these objects data types, and Scikit Learn cannot handle these, has no idea what to do with these. Everything has to be numeric. Okay. All right, so now we've prepared our data for machine learning. And now we're going to export it into Numpy. So to export it into Numpy, we're going to go from pandas to Numpy. All right, so this is a pandas command, pop. We're going to take off the sale price. Pop removes the column, and it also returns that column's values into sale price. So we're going to do that. So sale price is actually one column of data, but it's still a pandas object. It's called a pandas series. To get into Numpy, this is important. You have to use the values array, or the values attribute, excuse me. So I'm going to convert the sale price into values. And by convention, we use X and Y, and that'll help you remember that we're in Numpy now. So now that I've ran this, I know I have a Numpy array. And just to check, so these values are the same thing as was in the pandas series up here. And just to double check, we can do type of Y, and we're in a Numpy array. If we go back and do the type of the sale price, you can see we have a pandas series. Okay, so we need Numpy arrays. That's what we need, and we have a Numpy array. Now, we need to convert the remaining columns into X. So we remove that sale price. We want to get all these features into a Numpy array. And if we display this array here, you'll see what it is. So everything, X is now a Numpy array, and it's ready to use in Scikit-Learn. We can see the dimensions of this. So the X is a two-dimensional array, 1460 rows, 20 columns. Y is a single-dimensional array, and it just has 1460 values. All right, so we're ready for machine learning. Now, whenever I do machine learning, I always start with the dumbest model possible. And this helps form a baseline for how good my models are doing otherwise. So you have to have some way to compare your model to begin with. And so Scikit-Learn actually provides you a way to do the dumbest model with this dummy module right here. And it has a dummy for a regressor and has a dummy for categorical. So the dummy for regression problems, those are the ones with continuous targets, uses the mean as a default. So I'm going to import this dummy regressor into my namespace. Okay, so, and here's where we first learn about estimators. So dummy regressor is an estimator. This is our workhorse that's going to do our machine learning for us. All right, so let me run this line. So I've imported in dummy regressor. Now I'm going to do something called instantiating the estimator. So this is a common terminology in Python if you're used to object-oriented program. Dummy regressor is going to, we're going to create the actual estimator, and you can call this whatever you want. So I just named it dummy reg. The dummy regressor, you can choose what kind of strategy you want, like mean, median, or mode. Gives you different choices of strategies. I'm going to choose mean. So let me run this. So now I have my estimator. It's ready to go. it's ready to do its machine learning. Of course, it's going to do a very basic machine learning. All estimators have something called a fit method. So this is what you'll generally do after you instantiate your estimator. You're going to run a fit method on it. The fit method takes the input and the output and tries to learn, and it will produce a model. So here, I just ran that cell, and it's fit X to Y. Of course, it's a dummy, so it's actually not using any of the inputs. It's only going to take the mean of all the Y's. And we'll see this. So if we predict, all these estimators have fit, predict, and score methods, and several more, but these are the most popular ones and most common that you're going to use. So if we try to predict a sale price for each X, you'll see that all the sales prices are the exact same. They're just the mean. And we can double check that by just taking the mean using Numpy itself. And you can see that it's no different than what our dummy estimator predicted. All right, so how do we score this model? By default, the score method here will return the R² value. And by definition, using the mean as your predictor will always give you 0 for R², which is a very bad R². So we don't have any predictive value here. So our worst guess is just guessing the mean. We have to do better than the mean if we're going to do machine learning. So we have to get an R² higher than 0 in order to say that we've learned anything more than just the mean. Okay, so let's move on. All right, so a little bit on R². It just tells us how much better our model is than the dumbest model. Okay, that's in layman's terms. More technically, it tells us what percentage of the variance has decreased over the worst model. And I believe this picture below is a very good representation of what R² is. So it measures the percentage of area decrease from red to blue squares. So if you look at this red diagram, red squares over here on the left side, you'll see that R², if these points are our data, R² is simply the deviation from the mean squared. Okay, so this Y bar is the mean. So it's like saying we've guessed this for every single point. And we get this squared. If we square this, we'll get a term called the variance. How much do we vary from the mean? Now, if we fit a model, let's just say we fit a model right here on the square to the right, on the graph to the right, we'll see that our deviation from the line is now this much, and if we square it, we get this blue square. So R² is the reduction from the red to the blue. It's the percentage reduction from the red to the blue. That's what R² is. Okay, hopefully that helps you clear up R² a little bit. All right, so let's build a more complex model than just the dummy model that we just did. Let's do something simple like linear regression. Okay, so again, we're going to import the linear regression estimator. So the way Scikit Learn, the way you typically do import estimators with Scikit Learn is you go into one particular module. So Scikit Learn is broken up into something like 20 or more modules, each with their own, estimators. Okay, just based on what type of machine learning you're doing, whether it's a random forest or support vector machine or a linear model. They all have estimators that you can bring in to your namespace, into your notebooks. So here I'm just going to bring in the linear regression estimator. I'm going to instantiate it. That's the second step. So the first step is always import. The second step is instantiation. now I actually have my object that's going to be the actual estimator. All right, now instead of using all of our input data, I'm just going to pick one particular variable, and I want to see how well this one variable predicts sale price. All right, so I'm going to grab the lot frontage variable, okay, and I'm going to store it inside of x, this variable x, and I'm just calling it LF for lot frontage, okay, and I actually need to do dot values to get the make it a Numpy array. And notice it's a two-dimensional array. It's a little trick you have to do in pandas is actually wrap it in a list, and therefore you get a two-dimensional array because Scikit Learn does not handle one-dimensional Numpy arrays. Okay, so now that I have my data, my X data, I'm just using one of the columns. I can fit it. Y has stayed the same. Nothing has happened to Y. It's still the sales price. And then I didn't run the first one. So I have instantiated my estimator, and now I will fit. And let's run a prediction again. I'm going to save the prediction into this variable called ypred. So I've ran this predict method after I fit, and we can see that now the values, we no longer have the mean as our prediction. We have some other number. Whether or not it's any good, we'll find out with the score method, which defaults to scoring this by r squared. So how much has our variance shrunk? How much closer have we gotten? So we've shrunk our variance by 11%. That's what this means. So the best you can do is 1 with r squared, and that would shrink your variance by 100%, which means you would get everything exactly right. So here we've shrunk our variance by 11%, which is not particularly high. And we can see how much better we've done by plotting the prediction versus the actual y. So you can see that our prediction is actually on the x-axis over here, and our actual is on the y. And if we were to get everything completely correct, we'd have a straight line, but we don't. So we have some explanatory power here. There's some sort of pattern going up here when we plot our prediction versus when we plot the prediction versus the actual. All right, so that's a simple model with using one particular feature, a linear regression model with one particular feature. So let's go and use a better predictor. So we saw that the living area, when we graphed it, already had a much better, looked like it has much better predictive power than some of the others. So I'm going to save this into a variable called x area. And again, I need to do dot values to put it into a Numpy array, although it still handles your data even though it's in pandas, but I suggest putting it into Numpy because that's how all the examples are written in the documentation. So I'm still using my same model. I didn't have to instantiate it again. It's the same model. You can if you want to instantiate it again, but we don't have to. We're going to fit it, then predict it, and then score it again, just like we just did. So I fit it, I predicted it, so I have new predicted values over here, and I'm going to score it. And now, lo and behold, I've taken away 50% of the variance. So that blue or that red square has shrunk by 50%. The area has shrunk by 50% on average. And if we run that same plot, you'll see that our prediction versus our actual is getting closer to a straight line. So this is a much better model than before. Okay, so all I did here was choose a different variable. All right, so why not, let's just use all of our predictors, okay? So we're going to use X, which again is all of our predictors. We're not choosing one particular predictor here. We're going to use the entire matrix, which is it's actually 20 columns long right now. So if we look at this again, that's X. So let's fit this, let's predict this, and then let's score this. And now we've gotten a much better model. We're up to covering 80% of the variance. And our line, our points are getting closer and closer to a straight line. So we're learning a lot more about our data set by using all the predictors. Now, if you know a little about machine learning already, you'll know that I've made a large mistake, and that is using evaluating my model on the same data that I trained it with. So machine learning really only cares about data that you have not seen before, so unseen data. And this is what we call test and train sets. So the only way to get a fair metric of your fair evaluation of your machine learning is by evaluating it on data that you have not seen before. So this all this does is put half the data into this X train, Y train, and the other half into X test, Y test. And you'll have to just trust me, that's a little bit of Numpy slicing that will do that for you. And if we look at X test and X train, you'll see that it's actually perfectly split into 730 rows. So now what I'm going to do is I'm only going to fit my data on half, or fit my model with half of the data, just on X train. And I'm going to score it on the other half. Okay, so I've already built the model. It's going to take this X test, which it has not seen now. So it's only fit on this training set. It's not fit on the test set. And I will evaluate it against, of course, the Y test, which is the answer. And I'll see that my model is actually decreased in performance. So, which is going to happen when you look at new data. So your model can only really do as well as the data that it has seen. So you're going to see some performance degradation whenever you train on data that you have not seen. So it has slipped a little bit. So this original 80% R squared is not accurate at all, and giving us a much brighter look than what we would expect in the real world if we were to predict a new house. We wouldn't get as good of results. Okay, moving on. Okay, so what we did originally when we started out was called overfitting. So we were fitting our data. We were fitting our model to the entire data set. We were not holding out data to test with. So machine learning only counts on data that you have not seen. We don't care about how well you can do on historical data. This doesn't give us a good way to evaluate how well your machine has done. And the reason is because you can memorize all the inputs and outputs of your historical data. And when you see unseen data, that won't work, because unless the inputs and outputs happen to be the exact same. So the main purpose of machine learning is to be able to use our model with unseen data. Overfitting is akin to memorizing all the answers from a practice exam and expecting to do well on the real one. Okay, so like I said, machine learning models are evaluated on data that they have not been trained on. All right, so one way to do this, and I'm just going to talk about one way, is called k-fold cross-validation. And this is very common, and one of the best ways to validate your model, to see what it would do in the real world. And the way we do this is by chopping the data set into k different folds, basically just k different subsets of data. And we're going to train our data on all of them except for one, which we'll test it on. So we'll have a held out portion of data set. Here we have 5 folds in this particular image. All right, so Scikit Learn has this great function. This is not an estimator anymore. This is a function which will do k-fold cross-validation for us automatically, and it's a fantastic function. It's called Crossval Score, and it's in the model selection submodule. All right, and it's one of the most famous and popular functions in Scikit Learn. So we're going to import it into our namespace. Here we are instantiating our estimator once again. And the way Crossval Score works is you pass it the estimator, the X and the Y, and then you can give it a number of folds. Here I'm going to do 10. So there's a parameter called CV, and that stands for the number. It defaults to 3. Here I've done 10. So this will show us our score on 10 different subsets of data. And as you can see, they're mostly similar, but actually a few subsets like this one, it gets very poor results. But overall, it looks pretty good. And if we take the mean of this, we can see what we're likely to get in the real world, which is 75% reduction in our variance using our model. So Crossval Score is very good, and what you should use, what you can use to see what your model will do in the real world. Okay, so we used the dummy estimator and we use linear regression. Let's use something completely different like a decision tree. I'm not going to explain decision trees here. You'll have to look it up, but this is just how you get a different estimator. It's in a different part of the Scikit-Learn library. So we use the tree module and we'll import the decision tree regressor. And you'll notice that all the ones that deal with regression, or most of the ones that deal with regression, end in the word regressor. That's your clue that this does regression and not classification. Here we are instantiating it, okay? And we're gonna go straight to Crossval Score. We're not gonna do fit or predict or score. Crossval Score does the fitting for you, and it does the prediction and scoring. So it does all three for you, and it does cross-validation. So it's doing 4 things for you all at once in one single line. So you can see the scores. It actually does very poorly on one of the subsets of data. And if we take the mean from the decision tree and versus the mean of the linear regression, we'll see that it actually does much worse. Not much worse, but it does considerably worse than the linear regression. So it's a worse model. Now, random forest is based on decision trees. And this is yet another estimator, and it is typically going to always beat decision trees. So here we are again. It's found in the ensemble module. It ends in regressor. We instantiate it here, and we pass that object into the Crossval Score, and we get, lo and behold, we actually get a better score than our linear regression. So random forest beats linear regression with our current setup. Okay, so that's how you do other different estimators. You import them, you instantiate them, and then you can fit them and predict with them all through this Crossval Score function. So this is not an estimator Crossval Score, it's a function that takes an estimator and your data. Okay. All right, so we're going to move on to a slightly different data set, or actually a different data set to do classification. So classification is where we're trying to predict particular categories that each row will belong to. Particular discrete categories. The categories can be numeric, they can be strings, but they have to be discrete and limited to a certain number. Okay, so this is a credit card data set taken from the book Introduction to Statistical Learning. Here's the head of the data set, and we're going to predict whether each person here is a student or not. Okay, so we just want to predict whether the person is a student or not just by looking at all the other information that they have. So the first thing again, is do EDA and then replace missing values. Here, this data set has no missing values, so I'm just going to do some simple EDA. First of all, we can just look at the proportion of students and non-students in the data set, and it looks like it's about 70-30 split. If we look at the average age, it's kind of strange that the average age is just about the same for students and non-students. If we look at the average credit rating, they also have the same amount. If we look at the same balance, we see that actually students have a significantly different balance versus non-students. So this might be a very important feature in our model. Okay. Now, so again, we not only do we need to get rid of the missing values, but we need to binarize the categorical variables. But before we do that, in this instance, we actually don't have to binarize the categorical variables for the Y, for your target. You can leave them as strings. So here we're going to again pop, we're going to take the column out from the credit data frame, and we're going to convert it into Numpy array. And we can see that here's what Y looks like. And now we're going to do the same thing we did again to binarize all those categorical columns. We're going to use get dummies. And this time I actually saved it into a different variable, but you can use the same variable if you want. And here's the head of that data set. It's taken all the string variables like gender, married, and ethnicity and converted them into their own columns and binarized them. And you can see you'll just get zeros and ones for all these new columns that it's created. So this get dummies is extremely useful. This is still a pandas data frame, so we want to, like I said, convert this into a Numpy array. So we'll just get dot values, and that'll convert it to a Numpy array. Again, we need to do, I like to do learn with the worst estimator possible to see if I can beat that. So there is a dummy classifier, just as there was a dummy regressor. And I'm just going to pick the strategy that just picks the most frequent one as my guess. So the most frequent one in this data set is not a not a student. So if I didn't do predict here, but if we do predict, it's going to predict no for everything. And as you can see there, it's predicting no for everything. Okay. And if we score this, it looks like it does pretty well. It gets it right percent of the time. So this score method is returning the accuracy. What percentage are you getting the classification exactly right? So what times do they match exactly right? But this is just the same percentage as it's just guessing no every time. So it's going to get it right the same percentage that there are no's in the data set. So this is our percentage that we need to beat. So we need to be better than 73% with any machine learning algorithm that we use, or else we're not doing better than the dummy estimator. All right, so we want to beat this dummy estimator, and this is our baseline. So our baseline is different for classification than it is for regression. All right, so like I said, we need to beat this 73% accuracy. So usually the simplest classification algorithm is logistic regression, and it does say the word regression, but it actually is used for classification. So we're going to do the same exact thing. There's no real big difference between regression and classification algorithms in Scikit Learn. So you instantiate it, you import it, then you instantiate it, then you can fit and predict. I'm just showing the first 5 predictions, so it doesn't have a long output here. And then I'm going to score this thing, and it turns out, wow, it's actually 99% accurate. So it does much, much better than the dummy estimator. So far we're happy that we've done a great job at estimating this. But the problem here is that we're overfitting. we're evaluating ourselves on the practice exam. So you're not usually scored in school based on how well you do on practice exams. You're scored on how well you do on exam material that you have not seen before. So we've seen all this data before, so we need to do some cross-validation. So we must use cross-validation, and here it does it all in once. So we're just using that same cross-val score function. It's great. We pass the estimator, we pass in our data, and we tell it here we're just doing 5 subsets because it's a smaller data set. And it still does very well, but doesn't do as well. So we're still getting 96% accuracy. So our model, there's very high predictive value in our model. It almost gets everything correct. Okay, this is the last thing I'm going to talk about, is parameter tuning. So our models, so far, we've just used the default parameters that Scikit Learn has provided for us. And so you might not know exactly what a parameter is. So let's talk about it with one particular example, such as k nearest neighbors. So if we go back to we're going to use our housing data set here, but we're going to use k nearest neighbors. And for k nearest neighbors to work, you have to provide it with the number of neighbors you want to use. By default, I believe, and you can, let's see here, it uses 5 neighbors. So I brought up the documentation string. So by default, it uses 5 neighbors, right? So you can change this, and this is the parameter I'm talking about. So, and you change the parameters upon instantiation. So when you instantiate an estimator, you get to choose the parameters. And if I look at the doc string, all these words you see here are parameters. You can choose the neighbors. You can choose the type of weighting to use. You can choose the algorithm. These are all different parameters that you use. Okay, and you can read in the documentation more about these parameters and how to choose them. So here I'm just going to set one particular parameter. I'm going to leave all the other parameters to their defaults. And you can see the defaults right here. They're after the equal sign. Okay, so I'm going to do this with 3 neighbors. So I've instantiated a k nearest neighbors with 3 parameters. And if you just print out or if you just output the actual estimator, you'll see the parameters right here when you print it out. So Scikit Learn will display it like this. All right, so again, I forgot to do values here. Again, let's go ahead and do some machine learning. Let's take our housing, let's put it back into our variable X. Let's put the sale price in Y, and then let's do cross-val score. So we're going to find out what its typical score would be. Its typical R-square would be. We're going to do it over 10 subsets of data. So we're scoring 57%, which is low compared to the random forest, which scored around 80%. Now let's do this again, but with 5 neighbors. Okay, so we're changing our parameters. We're tuning our model. We're slightly tuning our model here. And if we use more neighbors, we get a better model, better result. We're up to over 60%. Now, and if we do this again, we do this with 10 neighbors, we're all the way up to 65%. So it seems like we're doing better with more neighbors. Now, we could write a loop to loop over every single combination of neighbors, but Scikit Learn has built this in for us, this functionality in for us, and I believe this is one of my last slides. So you can automate this process, and it's called grid search. You can go through all the different combinations of parameters with grid search. And this actually works just like an estimator itself. So it's in the model selection module. And it's called Grid Search CV. CV stands for cross-validation. So let's bring this in. And the key, the way this works is you need to form a dictionary of parameters. The keys for the dictionary will be the name of the parameter as a string and the values will be all the different parameters you want it to check. So what I'm saying here is I want my k-nearest neighbors, that's the name of the parameter, n_neighbors, to check all the ones from 1 to 29, actually. That's not inclusive of 30. So it's going to look at through all those neighbors, and it's going to return to me the very best one. Which n am I going to use? How many neighbors am I going to use? So again, this is just a dictionary with the keys as the parameter name and the values as the the different possibilities you want to use. Okay, so I've created that dictionary. I'm now going to instantiate this grid search estimator. Okay, even though it's not a machine learning model, it's used the same way as any other estimator, but you pass it in your estimator that you want to use, which is k and n from the last slide, and then you're going to use this param grid, and you're going to give it your grid of parameters. Now, I can give it many more parameters if I wanted to, as many as I want to check, and it'll check every single combination, every single unique combination of parameters for me. It'll check. And it's doing cross-validation, so it's doing a lot. And this is a very expensive operation, so don't be surprised if this takes a very long time on your machine if you have lots of parameters. And actually I haven't fit it yet. So this is just instantiated, it just gets it ready. And then we do the same thing. We fit the model with our data, and and you'll see a little star here, so it's running. It actually took like a second to run. And it ran through all those combinations of n neighbors. And to figure out what the best estimator is, there's actually a attribute called best estimator, and it's a k-nearest neighbor estimator object. And you can see right here that it actually chose 15 neighbors. Okay, it shows 15 neighbors. Let me change that. Okay, so now if I run cross-val score, if I use the estimator, the best estimator, so this is the one with 15 neighbors, I should get the highest possible score. So this is going to be my best possible k-nearest neighbors. It'll be with 15 neighbors, and I can't get any better than that based on what this grid search is saying. I could change many more parameters and try to tune it even more, but for now, just tuning that one parameter, it's found that it was optimized at 15 neighbors. Okay. All right, so that was the last slide. Here's a quick summary. So basically, you're going to import the data with pandas. You're going to do some data exploration. Then you're going to prepare for machine learning. You're going to fill in the missing values, and you're going to binarize the category features with get dummies in pandas. You're going to export into Numpy by doing dot values, making sure that you store the data in X by convention. It has to be a two-dimensional numeric array, and Y has to be a 1D array. The values can be strings. Now that your data is in Numpy, you will use Scikit Learn to import an estimator. Definitely know whether you're doing regression or classification. It's based on your Y. Once you've imported your estimator, I didn't write this, but you have to instantiate the estimator. Once you've instantiated the estimator, you'll use the fit, predict, and score methods to see how your machine learning is doing. Or a better thing to do is use cross-val score to do cross-validation, which does fit, predict, and score and cross-validation all at once. So cross-val score, again, is doing fit, predict, score, and cross-validation all at once. And finally, if you want to tune your model even more, you can do grid search CV, and that will get you the best. That'll help you find the best possible parameters, which can make a big difference in machine learning. So that's my summary, and that's my tutorial for today. This covered Scikit Learn at a very high level. It covered the most basic and most important aspects of the library. Let's see if there's any questions. Okay. Can we use Scikit in .NET? You should be able to use it in .NET. I've never used it myself, so I won't be able to give you a more thorough answer, but it is the most popular machine learning library in Python, so I assume you should be able to get it working in .NET. Okay. Yes, this is recorded. Okay, audio lost. Okay. Shouldn't remove the outliers. Okay, yes, so outlier removal and detection, you may or may not want to remove outliers depending on the situation. I didn't cover outliers in this particular tutorial. If the outlier is bad data, then it certainly needs to either be corrected or removed. If it is good data, then it needs to stay in there. You can even possibly have multiple models that work on different portions of your data, depending on whether or not you believe your current line is an outlier or not. Okay. Yes, the notebooks. So if you look in the chat, hopefully you'll be able to see that. And it was recorded. Okay. Yeah, so if you're using cross-val score, you don't have to worry about the whole splitting of the data sets yourself. It's all done for you behind the scenes, and that's what's great about cross-val score. Scikit Learn does give you tools to do a lot of this stuff manually. So there's a lot more to the library than what I just showed you. I just showed you the best features that can get you going right off the gate and the stuff that you can use over and over again. There are hundreds more things you can do in Scikit Learn, and if you want to learn more, I would encourage you to go to Scikit Learn and the documentation. And if you want to see more about what's possible, you can look at the API reference, which just basically contains everything that's possible. And you can see all the different, and this kind of helps you get you an overhead view of what's going on in Scikit Learn. You can look at all the different modules. Like for instance, this is the clustering module. You can see all the types of clustering you can do. You can see, let's see, there's all sorts of matrix decomposition you can do. There's all sorts of ensemble estimators and so forth. So this is a good page, and I can link this in the chat. So you can go visit there and see everything that's possible in Scikit Learn. So that's it. There aren't any more questions, so I'm gonna go ahead and end this. Be sure to leave comments. You can in the video or questions, or find me on Twitter at Ted Petrou, and I'll be happy to answer some questions there. All right, checking out. Hope you guys enjoyed it.
Thanks, Ted.